Hi, I'm Lydia.
And I'm Brian.
Hi there, David's here. We are going to explain a strategy that can be used to design databases. At first, it can be a bit scary since we have to deal with open problems. To make it simple, this video proposes a strategy. This strategy distinguishes two moments: before everything starts, and when everything is working. The following examples may help to understand this.
Example 1. A database for a chess competition.
Moment 1 is before the competition starts. There's a lot of data we must register, like inscriptions. Moment 2 comes once the championship starts. We must record everything that happens during the competition, like matches and results.
Example 2. An airlines company. Moment 1 is before we start flying. We have to buy planes, hire pilots, flight attendants, clients, airports. Moment 2 starts once we begin operations. We have to record everything: flights, payments, boarding passes, etc.
Now, let's explain the strategy. We start focusing on moment 1.
The first step is to make a list of objects and individuals.
For example, airplanes, pilots, flight attendants, clients, and airports. Once we have that list, we must ask ourselves, is there any direct relation between those objects and individuals? A direct relation is of the kind author to book. No matter what happens, there will always be a relationship between them, for the sake of being a book. It may happen that we do not see any relation between the listed objects and individuals. No need to worry. We just continue to moment 2. It's now the time to ask ourselves, what are the things that happen when everything is working?
The second step is to list the relevant facts, events, decisions, and actions. For example, trips, pilot assignments, ticket purchases, cancellations, etc. In short, all the kinds of things that happen in the day-to-day of the company.
Let's illustrate it with an example. To do that, we must give a name to the event, then try to define it. Trip. 2 pilots and a few flight attendants employ a plane to fly from one airport to another. There is an event which is called trip. From its definition, we identify individuals and objects that are directly related to it. They are pilots, flight attendants, planes, and airports. So, those are the relations between this event and the other elements.
Another example would be a purchase of a trip. Purchase. A client pays for a seat on a particular trip. So it is clear that purchase events are related to trips and clients. Those are relations that should be reflected in our database design. Now, let's do the design.
The first step is the list of objects and individuals. Here we find airplanes, pilots, flight attendants, clients, and airports. We draw a rectangle for every item. 5 items, 5 rectangles, that's simple. Other objects and individuals could be added if necessary, but let us make it simple to start. At first, it's better to focus in what really matters.
Any direct relation between any two of those items? In this case, the answer is no. Otherwise, a line should connect the related items.
The second step is the list of facts, events, and decisions. We had found 2 things: trips and purchases. Trip. 2 pilots and a few attendants employ a plane to fly from one airport to another. So, trip has 4 relations with pilots, flight attendants, planes, and airports. We draw the rectangle for this item, and then the connections.
The second event is purchase. A client pays for a seat on a trip. We draw this item's rectangle with its 2 connections.
To make it correctly, it's capital that we give each item a name. Then define a single event, including only the actors and things that are directly implicated. For example, it would be incorrect to define purchase as clients buying for seats in a plane driven by a pilot from one airport to another. The problem here is that we include data from other events in the purchases definition. Actually, we are messing with the definition of trips, when we only intend to define purchase.
The definition that we gave at first is complete, enough and simple. Given the client and the trip of the purchase, is enough to get any other required data, like who's the pilot or what are the airports. It would be a nonsense recording again and again that information every time a purchase happens.
Finally, we only need to add to cardinality. What is it? It's what tells us the nature of every relation. As you are going to see, the method cannot be easier.
Imagine a relation between A and B. 1A. How many B's? Also, 1B. How many A's? And that's all. Let's do it. 1 trip. How many airplanes? Only 1. And 1 plane. How many trips? The answer is many, so we write down N.
A different one. 1 trip. How many flight attendants? Many. And 1 flight attendant. How many trips? The answer is also many. To avoid repetition, we use the letters N and M.
Okay, hope you got it. Because we are going to do it a bit faster with purchases, without explicitly making the question. Are you ready? Go. 1 trip, many purchases. And 1 purchase, goes for 1 trip. Also, 1 purchase, 1 client. But 1 client, many purchases. Anytime you feel insecure, you can make the questions to see it better.
Finally, we have 2 tricky ones. 1 trip, 2 pilots. And 1 pilot, many trips. It's tricky because cardinality cannot be 2n. But nm it's too much in this case. They are only 2, and always 2. So we just make 2 relations 1n. This is exactly the same with airports. 1 trip, 2 airports. But 1 airport, many trips.
Once we have all the cardinalities, we must add a diamond shape on every nm relation, and give it a name. We choose this name. Trips has flight attendants. Relevant attributes should be added, like, for example, departure in trips, which would be a date time. Other attributes are more obvious, like first name, last name, email, etc.
This design, which is a simplified entity relation diagram, can now be translated to a relational database, with its tables and foreign keys. The translation is easy, and it's explained in another video.
And it's finished.